Welcome to the Network Plus Prepcast, your dedicated audio companion for mastering every objective on the CompTIA Network Plus certification exam. This series is produced by baremetalcyber.com. In episode 99 of the Network Plus Prepcast, we introduce one of the most fundamental components of internetwork communication, routing. At its core, routing is the process of moving data between different networks. It operates at layer 3 of the OSI model and depends on IP addresses to determine the best path for delivering data. Routers examine the destination IP address of each packet and consult their routing tables to decide where that packet should go next. This decision-making process is the foundation of scalable network communication and is essential knowledge for any networking professional. Routing is critically important in network design because it defines the boundaries between subnets, local area networks, and wide area connections. Without routing, devices on different networks would have no way to communicate. In large-scale environments such as enterprise campuses or the public internet, routing ensures that traffic flows logically and efficiently across vast and complex topologies. Routers determine how data reaches its destination, and their configuration directly affects the availability, speed, and reliability of communication. Understanding routing is vital for answering exam questions about network topology, device behavior, and communication paths. Routing and switching serve different but complementary roles in network operations. Switching functions at layer 2 using MAC addresses to forward traffic within a single local area network. Routing, on the other hand, operates at layer 3 using IP addresses to forward traffic between networks. Switches maintain MAC address tables and are concerned with local traffic. Routers maintain routing tables and direct traffic across broader networks. Recognizing the difference between these roles is key to understanding device placement and behavior in a multi-layered network environment. When a router receives a packet, it consults its routing table to determine the next hop. The table contains a list of known destination networks and the interfaces or next hop addresses to reach them. The router compares the destination IP address of the packet to entries in the table and selects the best match. Once the match is found, the router forwards the packet out the appropriate interface. This process happens in real time and is critical to maintaining efficient data flow across the network. Routing tables can be populated using either static or dynamic methods. In static routing, administrators manually enter routes into the routing table. This method provides full control and is suitable for small or simple environments. However, it does not adapt to changes in network topology. Dynamic routing, by contrast, uses routing protocols to automatically learn and update routes. This approach scales better and adjusts to changes such as link failures or new network segments. The exam will expect you to understand the trade-offs between static and dynamic routing and when each is appropriate. One of the most important tools in routing is the default route. This is a special route that acts as a catch-all for any destination not explicitly listed in the routing table. It is often used to direct internet-bound traffic to a single gateway, simplifying routing configurations. In small networks, a default route may be the only route needed. In larger networks, it complements other specific entries by handling unknown or infrequent destinations. Recognizing how and when default routes are used is an important part of routing design. Routing metrics help routers choose the most efficient path when multiple routes exist to the same destination. Metrics may include hop count, bandwidth, latency, or other factors. The route with the lowest metric is generally preferred. For example, in routing information protocol, the metric is based on hop count, while in enhanced interior gateway routing protocol, metrics consider bandwidth and delay. These values influence the router's path selection and help maintain optimal performance. Understanding how metrics affect routing decisions is essential for interpreting behavior during exam simulations or troubleshooting questions. Path selection in routing depends on several logical rules. One of the most important is the longest prefix match. This means that when a packet matches multiple routing entries, the route with the most specific match, typically the one with the longest subnet mask, is chosen. Another concept is equal cost multipath, where multiple routes with identical metrics are used simultaneously to balance traffic. Route aggregation combines several smaller routes into a single summary entry, reducing the size of the routing table. These techniques support scalability and are frequently addressed on the exam. Administrative distance helps routers prioritize routes, learn from different sources. Each routing protocol is assigned a value that reflects its trustworthiness. Lower values indicate higher trust. For example, a directly connected network has an administrative distance of 0, while a static route has a value of 1. Dynamic protocols have higher values such as 90 for EIGRP or 120 for RIP. When a router has multiple routes to the same destination from different protocols, it uses administrative distance to choose the best one. Understanding this concept is important for interpreting routing behavior in mixed environments. When a router forwards a packet, it updates the frame's MAC header but preserves the IP header. This process is known as packet encapsulation at layer 2. The router strips off the original frame header, adds a new one for the next hop, and sends the packet along its way. The IP header, which contains the destination address, remains unchanged. This allows each router to make forwarding decisions based on the original destination, even as the packet travels across different media and devices. The structure of a routing table is essential to understand. Each entry includes a destination network, a subnet mask, a next hop address, and an outbound interface. The destination and mask define which packets the route applies to. The next hop is the IP address of the next router in the path, and the interface specifies which port on the current router to use. This combination allows the router to make fast and accurate forwarding decisions. The format of routing tables and how entries are interpreted is a frequent subject of exam questions. For more cyber content and books, please check out cyberauthor.me. Also, there are other podcasts on cybersecurity and more at baremetalcyber.com. Routers are responsible for evaluating every packet's destination and deciding the best path forward. They play a decision-making role based on the current routing table, the state of interfaces, and available metrics. When a router receives a packet, it scans its routing table, identifies the most specific and reliable match, and forwards the packet through the corresponding interface. This evaluation process is continuous and affects every data flow that crosses network boundaries. Routers also track active connections through their forwarding and connection state tables, ensuring that replies and responses take the expected path. Routers learn routes through several sources. Static configuration allows administrators to define fixed paths, which is ideal for stable and predictable traffic patterns. Dynamic routing protocols, such as OSPF or EIGRP, enable routers to communicate with each other and automatically share path information. These protocols detect changes in network topology, such as link failures or new links, and update their tables accordingly. Additionally, routers recognize directly connected networks, those physically attached via interfaces, which are automatically added to the routing table without further configuration. To perform their functions, Layer 3 devices require proper addressing and awareness of their environment. Each interface must have a unique IP address that fits within the corresponding subnet. The router also needs to maintain knowledge of its neighbors using mechanisms such as Address Resolution Protocol for IP version 4 or Neighbor Discovery Protocol for IP version 6. These tools enable routers to determine which MAC addresses correspond to specific IP addresses on the local segment, allowing them to forward packets to the correct next-hop devices efficiently. In environments using virtual local area networks, or VLANs, routing between segments requires a Layer 3 capable device. Inter-VLAN routing allows traffic to move between different VLANs using router interfaces or switch virtual interfaces, also known as SVIS. A switch configured with routing capability can perform this function internally, eliminating the need for traffic to leave the device. Each VLAN has its own subnet, and the router or Layer 3 switch facilitates communication between them. Understanding inter-VLAN routing is important for recognizing how network segmentation interacts with address scope. Common routing errors often result from misconfiguration or missing information. If a destination is not present in the routing table, the router will drop the packet or send it to a default gateway if one is configured. An incorrect subnet mask can cause a router to misinterpret address ranges, sending packets to the wrong destination or rejecting them entirely. Interface down conditions, where a physical or logical interface becomes unavailable, also result in route invalidation. Identifying these problems quickly requires a firm grasp of routing behavior and the ability to read and interpret routing tables. Routing loops are another challenge that must be addressed through proper design and protocol configuration. A loop occurs when a packet is continuously forwarded between routers without reaching its destination. To prevent this, routers decrement the time to live, or TTL field, in each packet's IP header. When the TTL reaches 0, the packet is discarded, avoiding indefinite circulation. Routing protocols also include built-in loop prevention mechanisms, such as split horizon, route poisoning, or hold-down timers, depending on the protocol used. These features ensure that incorrect routing information doesn't result in instability or infinite loops. Several diagnostic tools help administrators verify and troubleshoot routing functionality. Traceroute reveals the path a packet takes to its destination, showing each hop along the way. This is useful for identifying where traffic may be delayed or misrouted. The route command displays the current routing table, helping to verify whether a destination has a valid path. Ping tests basic reachability, confirming whether a host responds to packets. Together, these tools provide a comprehensive view of how routes are constructed and followed, which is essential for both day-to-day management and exam readiness. Routing fundamentals form the basis for more advanced topics in network communication. From path selection to protocol behavior, understanding how routers make decisions allows administrators to design reliable, scalable networks. At Layer 3, devices evaluate destination addresses, consult their tables, and forward packets accordingly. Their behavior defines how subnets interact and how remote destinations are reached. By mastering routing principles, network professionals gain the ability to troubleshoot complex issues and optimize performance across diverse environments. To recap, routing is the process by which data is moved from one network to another based on destination IP addresses. Routers use routing tables to evaluate packet paths, rely on metrics and administrative distance to choose between options, and forward traffic based on interface and next-hop logic. They support inter-VLAN communication, prevent loops, and adjust to network changes through dynamic protocol. Routing is essential to modern network design and is a foundational concept that will appear in many scenarios throughout the Network Plus certification exam. Thank you for listening to this episode of the Network Plus Prepcast, your trusted audio guide to the CompTIA Network Plus certification. This episode was produced by baremetalcyber.com. For more cybersecurity podcasts, books, and resources, visit baremetalcyber.com. Thanks for joining us for this episode of the Bare Metal Cybersecurity Plus podcast. For more episodes, tools, and study support, visit us at baremetalcyber.com. And before you take the test, make sure to check out the practice questions in the book Achieve CompTIA Security Plus SY0-701 Exam Success by Dr. Jason Edwards. They cover every domain and are a powerful way to lock in your knowledge.